this personal thing, because you can get little bit idea how it is useful, this nanomaterial, and how these chemical methods are useful to synthesize this nanomaterial. Because before going to elaborate about the colorful solar cell as well as the supercapacitor, I am elaborating certain chemical methods. I am demonstrating certain chemical methods which is used in a simple way to make the material in a thin film form. But not only to make the material in a thin film form, but thin film can be embedded with the nanomaterials. So if you are using this nanomaterial for the technological application, you can say that is the nanotechnology from the synthesis to application part. So before going to the detail, just have the personal look. Just under my guidance, 16 PhD students they have completed. Some they are working like Israel, Korea, Spain, then maybe Institute of Science. And one just student, he got one very good fellowship called Marie Curie Fellowship. He is going to work in UK in collaboration with MIT USA. And he completed PhD in 2019. And just for information, he has completed about 3,000 citation with H index of 30. So you can use this method so that you can just get idea how the student can be get benefited of this method, not to just synthesize the material, but you have to apply that material. That is the most important part. So just these are the publications. Just to highlight that one, you can achieve good impact factor, good quality publication just by synthesizing nanomaterial for device grade application. So these are the just publication how year wise that we have published in our group. Not only this one, uh, just madam told about the citations as well as impact factor as well. And here this is just a project, 7 projects completed, and at present I'm running 3 projects. And if you see the title of each project, it is just not only to synthesize the material, but at the end it is a application part, either by means of solar cell, or maybe you can think about the sensor, that is the gas sensor, or the supercapacitor. So basically you can keep in mind whenever you are making the material as the nanotechnology, if it is having certain application, then it is a great achievement. So you can focus and target yourself to make the material in the nano form so that you can apply for the different application. Just I am going to elaborate about the 2 application, but you can think n number of applications, maybe photocatalysis, maybe luminescence, maybe gas sensors, right? Or maybe medical applications you can think of. Just to get highlight of this one, I am elaborating 2 approaches from synthesis to application. Then just madam told, just we published one book called Simple Chemical Method, how it is very useful to make the thin film deposition from the synthesis to application. And some sound is coming, madam. Okay, thank you. So this book, it is written in co-authorship with Dr. Inoy, with whom I worked in Germany, Dr. Gupta from USA, Professor C.D. Lokande, he was my guide. So Professor Gupta, he visited 3 months back to VNIT as well. So you can think yourself, all this it is there, which is based on the nanomaterial. So based on what? You can question yourself, can I do? How? By which method you can do that one? And how to apply for device grade application like maybe solar cell or maybe supercapacitor at the end. So you should get answer at the end about these approaches so that you can use this nanotechnology for different applications. Madam, some sound is coming, I think.
Excuse me, please, please mute yourself. Surendra Gupta, sir. Dr. Surendra Gupta. Ma'am, I am calling.
Can I proceed, madam?
Yes, sir. Please continue.
Okay. So nano, just maybe you heard many talks that nano, it is a Greek word that is called dwarf, which is a manipulation of the matter having size less than 100 nanometer. But I can suggest you regarding the quantum dot. At the next slide, you will get it the idea, so that you can make the quantum dots having size less than 10 nanometer approximately, we can say, which can change their properties, which plays very important role at the present technology or maybe in the future technology as well. So nanotechnology is the creation of useful or functional material or devices of any size, but that should be embedded the material in the nano form so that it can change the properties at the nanometer length scale. So just as the idea, water at the micro scale it is a lubricant, but when you are thinking about the water at the nano scale, it can be additive. One another good example is a cadmium selenide. So if you are changing the size of the particle without any doping, it is possible to alter the properties of the material. So basically, just as an example, as a cadmium selenide, if you are having the size, particle size is about 8 nanometer, it can be red. And if you are reducing the size because of the quantum size effect, it can change the properties, that is optical property, maybe it can be red to blue as well. So if you're reducing the size up to 2 nanometer. So this is one example that just by altering the size of the particle, you can change the property. Just this is optical property, but along with that one, it is possible to change electrical as well as magnetic property, right, or mechanical property. So that is the beauty of the nanotechnology. So physical property it is possible to change, chemical property also it is possible to change. Not only this one, you can change the electrical, mechanical, optical or magnetic property. So just as example, we can take gold, which is yellow in color. Without changing the gold, just change the size of the particle of the gold. It is possible to reduce the size of the particle, maybe for example 2 nanometer. You can reduce the melting point, which is above 1000 degrees Celsius to 500 degrees Celsius. And that is the beauty of nano, and that is the beauty of the quantum size effect, that is physics behind that one. So what is physics? If you are taking the material in a three-dimensional, which is called as a bulk, you can play with the density of states against the energy. Suppose whatever bulk it is there, that we can say in a three-dimensional, that is x, y, z axis can be there. So if you are reducing one axis, maybe z axis, that can be thin film. So you can think about two-dimensional, so that Dawes function against the energy is going to alter. Again, if you're reducing one axis, maybe y-axis, that can be nanowire. So you can play with the nanowire. And also, if you're reducing the third axis, then you can say that is the quantum dot. So size or zero-dimensional material, we can say. But all this either one-dimensional or two-dimensional, it in the one two-dimension in one dimension, or maybe zero dimension in two dimensions. What we are doing, we are taking the thin film in a two dimensions, so that can be embedded with one dimensions material, that can be embedded with zero dimensions material, so that you can alter the properties of thin film by embedding different size of the particle, different morphology of the particle, so that you can use and you can synthesize this one for the different application. So just as an example, as a decreasing the size, optical band gap, it is going to change, which is going to increase because of the discreteness in the energy level. So that is the beauty of this one. So this is just related to the optical property. You can play with the electrical property or different property depending upon your type of the application. So you can think whether it is so complicated to work on nano. So as you have seen, mostly Three Idiots movie, right? So what is the motto inside Three Idiots movie? Chase excellence, success will follow you. Chase excellence, success will follow you. So I have modified this one. Chase quantum, nano will follow you. Means try to make quantum materials, quantum dots, so that automatically you can get in your hand nano materials. So what to do? Try to do simple things in a simple way. Learn more, use to apply. So at the end, you can do much more complicated things by a simple way, so that it can be applicable for the society. That is the most important part that you have to focus, because nowadays, now you are thinking about the government strategies, they are coming, that is make in India, made in India, startup, all this is coming, because at the end you should have something in your hand that can be applicable for the society. So you can think whatever you are making, if it is applicable for the society, it is to have good advantage to publish papers, to have good advantage to have better projects, better patents, but at the end society should be benefited among your research. That is the most important concern in my talk. So what form may be there, based on what are the material source for the nanotechnology? That can be, you can make any material, you can take any material, maybe metal, semiconductor or insulator, but you can play with the size, that can be clusters or nanocrystals or quantum dots, or maybe nanowires or maybe nanotubes, depending upon the size, depending upon their diameter, the property is going to alter drastically. So you can get use of that one for making the device. That is my concern. So here I am going to demonstrate lab scale nanomaterial, how it is possible to achieve by using simple chemical methods, that can be solar cell or that can be supercapacitor application. So here you can think whether which method can be applied to make the nanomaterial. That can be nanoparticle, that can be nanowire, that can be quantum dot, which are embedded inside the thin film form. So basically, if you're thinking about making the nanomaterial, there are two approaches are there. One, it is called as a top-down approach, that can be crushing, grinding, ball milling, it will be there. But making the material by using this method, it is very difficult to have the same size as each time. Again, making the material less than 100 nanometer or less than 10 nanometer, it is much more difficult and it will be costly as well. So what we thought to use bottom-up approach called as a solution chemistry approach. So solution chemistry approach to make the nanomaterial in a thin film form. So materials in a thin film form, which is easy. I will demonstrate that one, and it is easy to make the material as well. Not only to make the material, you have to characterize that one, and then you have to apply that one for different application. So whenever you are thinking about any type of the diverse application, you should keep in mind 3 points. First point, it is there, that is the material. So whatever material that you are taking, that can be nanoparticle, that can be nanowire, that can be quantum dot, or different form of the nanoform may be there. But whenever you are making that material, whatever the process that you are going to adopt, that should be low cost, that should be simple. And whatever the raw material that you are going to use, that one, that should be easily available. Because whenever you are thinking about any device, at the end, device should be have a lower cost. If your material is very costly, or if your process is very costly, then making the device at the larger scale, it will be costly. So you can use this material in the different form, use the process that can be simple, right? But you have to tune the property depending upon the application. Just I mentioned that can be a thermal property, that can be electrical property, that can be mechanical property or optical property, or different properties like magnetic property may be there depending upon the type of the application. So this is the three major steps are there that you have to keep in mind whenever you are making the material for the different application. So you what we required, making the nanotechnology or nanomaterial, you required a synthesis, then you have to characterize that one, and then you have to apply that one. So you require a little bit chemistry background as well as the physical background. So both are going in hand, then it is very great. Not only this one, you should have the mathematical background as well if you are doing certain simulations. But at the end, this can be in the laboratory, but whenever you are making the device, it can be applicable for the society. You should have the engineering as well as the technology background, because whenever you are making anything in the laboratory, it should go to the industry so that they can fabricate at the larger scale, so that whatever process that you are going to adopt, that should be commercially available, commercially viable. So that is the most important aspect. So I am going to demonstrate certain few chemical methods. In that book, actually, we have elaborated 12 chemical methods. Different methods are there, but here I am going to demonstrate about few methods because of the time shortage, we can say. So here I am going to demonstrate about simple and low cost chemical method which can be applied to make the nanomaterial. So because whenever you're thinking about the chemical method, whatever the basic building blocks are there, these are the ions, so that you can control at the ionic level. You can control at the ionic level. So that is the most important thing. So you can have the bottom-up approach to make the nanomaterial for the synthesis. So here I am going to demonstrate about different methods that can be deep and dry coating method, that can be spin coating method, Dr. Blade technique, or spray paralysis, chemical bath deposition, as well as modified chemical bath called successive ionic layer adsorption and reaction method. So you can get a little bit idea about this method. You can think to use this method for making the nanomaterials for the different device grade application. Am I audible, madam?
Yes, sir. Yes, sir.
So first technique it is there, which is called as a deep and dry coating technique. So deep and dry means this is very simple technique. You can make the solution. What you required is the solute as well as the solvent, so that you can have the solute and solvent inside one beaker. You can take your substrate on which you are going to coat in a thin film form, the material in the thin film form, right? So you can take the substrate, you can dip that one inside this one, and then you can dry it. So this is very simple technique. So how it is useful? Just as an example, what we are doing, we are using carbon nanotube, which is commercially available, making the solution, taking the substrate, dipping inside the solution, and drying it. Dip and dry. So this is a very simple technique. It is there so that it is possible to coat the material on the substrate surface. So we are coating carbon nanotube on the substrate by using just deep and dry coating technique. So what you require? You require simply solute, solvent, and beaker and substrate. That's all. So you can make the material in a thin film form on whatever the type of the substrate that you want to coat. That is the beauty of this technique. So different thing it is coming up, maybe immersion, startup, drainage rate, continuous whether it is there, evaporation rate, that you have to count for this one. So what are the preparatory parameters? That can be concentration, what type of the solvent that you are using, what type of the solvent means, that can be aqueous, that can be non-aqueous solvent that you are going to utilize, temperature, what is the immersion, drainage rate it is there, and whether what type of the substrate it is there. Because substrate property plays very important role, whether it is hydrophilic or hydrophobic. Because if you are thinking to use aqueous solution, then if your substrate is not hydrophilic, if it is hydrophobic, it is not possible to get deposition on the substrate surface. So you can think about different preparatory parameter whenever you are making the material in a thin film form. Just as an example, this is carbon nanotube coated on different substrate like FTO, PET, glass, stainless steel, as well as PEC, PVC. So this is the image called scanning electron microscope image, and here you can see the scale bar. It is 300 nanometer. So you can see the beauty is that this carbon nanotube, it is uniformly coated on the stainless steel substrate. So inside this porous, it is very useful so that it is having high surface area, carbon nanotube coating on the substrate. So substrate surface, whether it is hydrophilic or hydrophobic, it is important. Also, sometimes it is required to have linker between the substrate and material to be deposited. Then you can ask yourself whether it is possible to coat polymer or carbon nanotube. So what we have done, we have just taken the solution, that is P dot PSS, that is polyethylene deoxythiophene, and we have dipped the carbon nanotube coated substrate inside the polymer, and here you can see that the solution get adsorbed on the carbon nanotube, and this is ACM image. You can see that very uniform coating of the polymer it is there on the carbon nanotube just by using deep and dry coating technique. So next technique it is there called as a spin coating. The name itself suggests spinning of the substrate and then coating. So this is very simple technique. It works with the force called centrifugal force, which is responsible for spreading of the solution which is on the substrate. So this is just spreading of the solution. It is there. Here you can see that if you take the drop at the substrate on the spinning uh, base, so that this solution gets spread, and whatever extra thing it is there, it is coming out. This is the actual process for the spin coating. So what it is there, these are the 4-step process it is there: adding of the gel, spin up process, evaporation, and spin off process. So this is very simple technique. It is possible to coat very thin as well as the thick film as well, so that you can go up to 10 nanometer or 5 nanometer as well as you can go up to 5 micron or 10 micron as well. So because depending upon how much RPM it is there and how much, what is the solvent or viscosity it is there, you can decide the film thickness. And whatever gel it is there, whatever solution it is there, it is possible to coat on the substrate surface. That is the idea. So basically, whatever spin coating technique it is there, they are going to use certain vacuum so that whatever substrate can be stick to the base called as a base seal. So here you can vary the RPM versus the time, that is called as the ramp rate it is there, so that you can have different thicknesses depending upon the parameter called revolution per minute versus time. So basically this cost of the unit can be about 1 lakh rupees, but if you have certain simply motor from the car tape like a car tape recorder, you can assemble this one with a different step voltage of maybe 0.5, 1, 1.5, so that it is maybe less than 500 rupees. So it is possible to start with, to make the nanomaterial in a thin film form, you can start with rupees 500 as well. But if you are doing much more complicated things, you require the programmable spin coater. That is no doubt. So what are the preparatory parameter? Concentration, solvent, temperature, rotation speed, and type of the substrate. These are the important parameter inside the spin coating. Just as an example, we have coated TiO2, that is titanium dioxide, by using spin coating technique. So what we have done, we have used P25 titanium dioxide nanoparticle and used certain solvent like acetyl acetone or ethanol, as well as titanium isopropoxide. And this is the same image how uniformly at the 5 nanometer scale bar titanium dioxide can be uniformly coated on the substrate surface. And also we have calculated the surface area. So it is possible to make oxides, it is possible to make and coat any material which is having in the gel form. So you can coat the polymer, you can coat the metal oxide, metal chalcogenide by using this technique. Next technique it is there called as a doctor blade technique. So this is very simple technique it is there. So what you required? You required simply gel for the material to be deposited. You require Tixo tape, glass rod, and the substrate. That is very simple technique it is there. This is like a chapati making in your house. But it is, if you are making something, you should be very precise about the preparatory parameter. So what you can do, on which substrate you want to coat, you can take that substrate, add the Tixo tape at the both the end, so that Tixo tape thickness plays very important role. Then you can add the gel in between, take the glass rod and just roll it. So whatever the because of the rolling, this gel it is get uniformly dispersed between these two Tixo tape area. Then you can take out this Tixo tape, so thin film it will be deposited. So depending upon your gel, what is the particle size it is embedded inside the gel, it will be coated on the substrate surface. So this is very easy technique to make the nanomaterial on the substrate surface for different application. So TiO2 can be used for different application, medical application, you can use for solar cell, you can use for photocatalysis, you can use for gas sensor, different application of the TiO2 it is there. Not only TiO2, whatever it is possible to form the gel, it is possible to coat by using this technique. So what are the instrument you required? You require only just substrate, Tixo tape, and the glass rod. That's it. And the gel for which you are going to be deposited. So this is very simple technique. So this is titanium dioxide we have coated on the substrate surface, and this is just room temperature deposition. It is there. But suppose if you are having certain hydroxide, it can be coated, it can be taken out with the annealing effect. And here you can see that depending upon your expertise, depending upon how much you are pressing, depending upon the thickness of the Tixo tape, thickness can be varied. So here we have deposited about 6 to 7 micrometer titanium dioxide on FTO coated glass substrate. And here you can get idea in the cross section mode how it is uniformly deposited on the substrate surface. What are the preparatory parameter inside this one? Yes, the concentration, type of the raw material used, solvent, temperature, thickness of the Tixo tape, what is the type of the pressure, and then substrate use. So any material that can form the gel, it is possible to coat on the substrate surface. Also polymer, you can mix with titanium dioxide or different metal oxides also, or single polymer also, it is possible to have in the gel form, it is possible to coat on the substrate surface. Next technique it is there called as a spray pyrolysis. So this is also simple technique it is there. What you are doing is the spray and pyrolysis, means pyrolysis of the solution. That is because of the thermal decomposition. So you are taking the substrate at the higher temperature. Then you are spraying the solution. Solution contains solvent as well as solute, so that you are heating the substrate at a higher temperature. Because of that one, solvent gets evaporated and you are getting the film on the substrate surface. So this is from the hallmark, but we have developed in the laboratory as well, so that you should have the mechanical system. It can move in the x direction, y direction, or maybe z direction, what type of the nozzle it is there, then that you are spraying. So basically this spray pyrolysis can be widely used for making FTO. FTO is called fluorine doped tin oxide coated glass substrate. As glass, it is a amorphous, but for the solar cell application or for the photonic application, we require the substrate should be transparent as well as conducting. Metal, it is not transparent, but it is conducting. Glass, it is transparent but non-conducting. So what it has to do is to coat very thin layer of the oxide on the glass substrate, which can be conducting. So what we have done, we have coated tin oxide on the glass substrate. And here first image you can see that this is a glass, and second one is the fluorine doped tin oxide having the sheet resistance less than 20 ohm per centimeter square with the transparency 90%. So you can do FTO, you can do ITO by using this technique. Just to get idea, I am elaborating that one. So this technique it is there, which can be used to make FTO as well as different metal oxides. So here you can see this FTO that is on a conducting substrate, which is very uniformly coated on the glass. Here you can see at the scale bar of 300 nanometer, very uniform coating can be done. And that's why it is showing the transparency more than 90%. This is the cross section image, so that you can see the thickness of this FTO, it is less than 100 nanometer. So it is possible to have the FTO with very less thickness. That's why it is a transparent. So what are the preparatory parameter inside this one? You can think about concentration, you can think about raw material use, solvent, temperature of the deposition, type of the nozzle, gas pressure used, and substrate use. So different oxides, different sulfides, different selenide, different tellurides also it is possible to make on the substrate surface. But added advantage is that you can get very uniform as well as adhesive film because of this spray pyrolysis. But disadvantage is that evolution of the toxic gases. So each method it is having its own advantage as well as disadvantage. Next technique it is there, it is called as a chemical bath deposition technique. So chemical bath means what? You can have the cation and anion together mix inside the beaker, and then you can dip the substrate inside this one. You can heat the solution or not heat the solution. You can stir the solution or not stir the solution depending upon your preparative parameter. So this is very simple technique. You can have only beaker, solvent, solute and substrate. That's all. Sometimes you require the heater so that you can heat the solution maybe for example 70 degrees Celsius or maybe 80 degrees Celsius, so that this simple technique can be used to have variety of your materials. So what are the preparative parameter? Type of the substrate, you can do the doping, pH, composition, stirring, cation, anion, concentration, their ratio, temperature, deposition time. These are the preparative parameter. It is possible to adjust inside this one. So this is very simple technique it is there. So this is very simple and low cost, and this is possible to have large area deposition as well. So you can deposit sulfides, you can deposit selenides, you can deposit different chalcogenide or oxides by using this technique. So this is very simple technique to make the material in the nano form. So another technique it is there. In the previous chemical bath deposition, you are mixing cation and anion together, and you are getting the material on the substrate surface which is very low. So wastage it is more, about 99% wastage it is more. So that can be possible to avoid by this modified chemical bath deposition called successive ionic layer adsorption and reaction. So whatever you are doing here is, instead of making cation and anion together, you are placing cation and anion separately. That is the basic idea. So you are getting the reaction only on the substrate surface, not in the solution ideally. For this one, you are using ion exchange water between this cation and anion, so that there is no precipitation occur inside the solution. So it is possible to use the solution for many times. So what you have to do, for example, I want to deposit cadmium sulfide. So you can take the source for the cadmium sulfide as a cation, maybe cadmium sulfate, cadmium acetate, cadmium nitrate, for example. And then anionic source, maybe sulfur source, you can make like Na2S, sodium thiosulfate, thiourea, thiocetamide you can take. Then you can take the substrate deep inside the cationic solution. So cation gets adsorbed because of the van der Waals force of attraction on the substrate surface. And then you can rinse this one inside the solvent that you are going to use, for example water, called as a ion exchange water. So unadsorbed ions are removed out. Then take this substrate deep inside the anionic solution, so that cation gets reacted with anion, so that there is a one monolayer formation on the substrate surface. So cation and anion reaction it will be there on the substrate for the formation of the one monolayer on the substrate surface. So for example, CD2 plus you are taking reacting with the S2 minus ion. So CDS one monolayer it will be there on the substrate surface. So the beauty of the technique is that you can control at the ionic level. That is the beauty. So that one monolayer control it will be there inside this technique. So depending upon quantity of the ion exchange water used and whatever the concentration of the precursor that you are going to use. So this is very simple technique, and this technique is widely used to make the quantum dots. So depending upon number of cycle, you can vary the thickness, you can vary the size of the particle. So that is the beauty of this technique. So this is a cellular unit which is now fabricating by a company called Hallmark. So instead of four beaker, you can have the six beaker system. So here thickness can be controlled depending upon number of cycles. So you can have maybe 50 cycle, maybe you can have 100 cycle. But suppose if you are doing maybe 500 cycle or 1000 cycle, it is very difficult to sit at one time and they do the deposition. Then you can use this microprocessor control unit so that you can have the maybe cycle maybe 500 or 1000 cycle, and for each beaker it is possible to control stirring. In each beaker it is possible to control the temperature of the solution. So it is possible to have different preparatory parameter so that you can have one material but having a different morphology also it is possible to get depending upon type of the source that we are going to utilize and type of the preparatory parameter that you are going to utilize. That is the beauty of this technique. So what it is possible to deposit different oxides, different sulfides, different selenites, different tellurides also it is possible to deposit by using this technique. So added advantage is that wastage is very less as compared to the chemical bath deposition. So you can reuse the solution for many times. That is the beauty of this one. Now just I have demonstrated the different methods, how it is there, how you can make the material in a thin film form. So how to use to make it for the nano. Just to get the idea, I'm elaborating two things. One, it is for light to electricity conversion called solar cell. So solar cell, as we can have unlimited source of energy, that is the sun. We are not paying for that one, but we can utilize free of cost. So how to utilize that one and how to make the solar cell in the laboratory. So I am going through this one called the concept called dye-sensitized solar cell. So you can understand the concept for this one. So because whenever you are making any device, your concept should be very clear. Then your methodology should be very clear. Your steps that you are going to be adopted, that should be very clear. So what are the preliminary requisites? It is required either for the method, either for the deposition, either for the material, and what are the property requirement is there, that should have clear in mind. Then and then only it is possible to fabricate the device in the laboratory. Otherwise it will be very difficult, because technically you will face a lot of problem whenever you are making the device in the laboratory. So working with the device, what is the advantage? Making the material in the thin film form, that can be nano, you can characterize that one, you can publish that one. But whenever you are making that one for any device grade application, you will get certain satisfaction. Means if you are demonstrating something, whether your device is working, then you will have added advantage as the satisfaction. Means publication is the one part, and second one satisfaction is the another part. That is most important, and whatever you are making that one, that should be applicable for the society, which is the most important target that you can make yourself. So automatically you will get the publication. That is the another thing. So you have seen many type of the solar cell, right? That can be silicon, that can be copper indium gallium sulfide, that can be gallium arsenide, right? But this type of the solar cell are either black in color or blue in color, and fabrication cost it is very high. So here I am going to demonstrate about one type of the solar cell called a dye-sensitized solar cell, which are cheaper as compared to this type of the solar cell. So here what our approach that we did, just to get the idea how to make the material and how to characterize and how to apply that one, that is the most important concern that I'm going to elaborate, so that you can work on the nano for the different application. So I'm going to demonstrate about the colorful solar cell. That may be new for you, right? So it is based on the concept called dye sensitized solar cell. The process, it is low cost and low temperature process that we are adopting to make the zinc oxide, so that it can have attractive application along with the sharp cut in a production cost. So our approach, we are thinking to have the flexible substrate. So it is possible to bend the solar cell, but we have not succeeded to that point. So what we made, to have certain targets, to have the colorful cell or solar cell, to see through. If it is flexible, then it is great. Cheap, depending upon type of the deposition, and if it is lightweight, so that you can hang that one where you want. So that is the target we made for this type of the solar cell. So how this dye-sensitive solar cell works? That is the most important. You should understand the concept for this one. So what are the basic requirements? So you should have TCO. Just I mentioned transparent conducting oxide, which can be coated on the glass. So for the solar cell application, glass is non-conducting. You have to make the glass conducting. What you can use? You can use, for example, spray pyrolysis technique, or nowadays commercially available FTO. It is available commercially, or ITO is also available commercially. You can have that. You can take the TCO glass, and here you can see that these white balls are there. These are the titanium dioxide nanoparticles. So basic requirement for the dye-sensitive solar cell is one material is a wide band gap. So wide band gap material should be there. It should have high surface area. It should have interconnection of the nanoparticle. That is the most important parameter. So here interconnection of the nanoparticle, wide band gap, and uh, material which can be coated on the tissue should be there. Then on which you can coat one monomer of the dye. So dye, it is responsible for absorption of the light, not this wide band gap material called TiO2, or you can use zinc oxide having the band gap greater than the 3 electron volt. So whatever visible part it is there, it can pass through this TCO glass, it can pass through this wide band gap material, it can fall on one molar of the dye. Then you can place the liquid electrolyte and back on contact as the cathode TCO glass. So mostly platinum coated glass, it is used as a TCO, very thin layer of the platinum coated, but now this carbon or graphite or carbon nanotube or other metal chalcogenerics are going to use, and people are working on that one to reduce the cost issue, because platinum, it is very costly. So this is the schematic representation of the dye-sensitized solar cell in the cross-sectional mode, how it can observe. But you have to understand on the basis of energy band diagram. That is the most important. So what it is there for TiO2, you should have conduction band and valence band, then dye, homolumo, and their electrolyte. So if you are illuminating with the visible light, this visible light excites the electron within the dye. The electron go to the higher energy level, it can transfer to the energy level of the TiO2, and this electron will pass through the external circuit and it will go to the electrolyte. So this cycle, it is completed, and electricity can be generated. So here in a simple way we can understand that one on the basis of the schematic. Here I have represented that one. So you can illuminate light, visible light. Then here you can see that this blue, it is there, blue dot, it is there. It is just, we can say this is the electron. It is generated within this dye molecule, transferred through the wide band gap semiconductor to the TCO towards the load and towards the electrolyte. So one requirement for this wide band gap is the interconnection of the nanoparticle, because whatever electron it is generated within the dye, it has to transfer through the wide band gap semiconductor, and wide band gap should not absorb the light. Which material it is necessary to absorb the light is the dye. So dye, it is responsible for the absorption, which is responsible for the generation of the charge carrier. So whatever charge carrier generated, it should pass through the TiO2 to the TCO towards the load, towards the electrolyte, and this cycle, it is completed and electricity is generated. This is a simple way how we can understand this dye sensitized solar cell. Now this world record efficiency, it was achieved about 11% in 1991, and now it is reached to about 13 to 14%. Not much, that much step it is there inside this efficiency. So new concept it is now coming up, that is called as a perovskite type of the solar cell, or other type of the solar cell are there. But you can think about the stability. Perovskite, it is having stability issue. So what we thought to work on the dye-sensitive solar cell, but not using TiO2, but using zinc oxide. So how we have made the laboratory scale solar cell, that I am going to demonstrate. What it is there, you can have the glass, you can have TCO, then we have used seeded zinc oxide, and then nanoporous zinc oxide, then dye, then electrolyte, then back contact. So why we required this flat zinc oxide or seeded zinc oxide? Because here interconnection of the wide band gap material is required. As interconnection of the material is there, and it should have a very high surface area, it can be nanoporous or microporous. So it is having certain porous, and because of the porous, this electrolyte can penetrate through this porous, it can touch to the tissue, and your device can be short. So to avoid that one, we have used seeded zinc oxide or flat zinc oxide. So how we have developed? We have taken TCO, we have deposited zinc oxide, that can be, we can say, seeded zinc oxide or flat zinc oxide. Then nanopore zinc oxide, on which we have coated sensitizer as a dye. Then liquid electrolyte, then back contact, and then device testing. This is the stepwise development we have adopted in the laboratory, so that whenever you are thinking about any device grade application and development, you can think how to develop stepwise in the laboratory. That is the most important aspect that I am going to elaborate. So first step, that is TCO. We already know that spray pyrolysis can be used to make FTO, but nowadays you can use this TCO commercially available. Then how we have deposited zinc oxide. So we have used for seeded zinc oxide, Scalar method, just I explained for CDS. So what we have used for CDS, we required cation as a cadmium source and for sulfur as a sulfur source. But for zinc oxide, one is oxide and second one is the zinc. So cationic solution is the zinc acetate complex with ammonia that we have used, and for oxide we have used just water at high temperature, that's all. So water kept on a hot plate. So what we have done, we have taken FTO dipped inside the zinc acetate complex with ammonia solution. So there is adsorption of the zinc ion on the substrate surface. We have taken that one and dipped inside the this water at a high temperature. So there is a formation of the zinc oxide as well as hydroxide on the substrate surface called FTO. But for dye-sensitized solar cell application, you should have oxide which can be pure. Pure means what? Without any hydroxide part. That is the most important part. So for that one, we got hydroxide some part inside that one. So we have annealed that one at 200 degrees Celsius. But if you are using titanium dioxide, you have to anneal that one at 450 degrees Celsius. So we have reduced the temperature for this zinc oxide, keeping in mind to have the flexible substrate, so that you can use PET coated ITO so that you can bend the solar cell. But we have not succeeded that one. But still, we have reduced the temperature up to 200 degrees Celsius by proper optimization. So we got pure zinc oxide. And here, this is the X-ray diffraction pattern just to understand whether zinc oxide it is deposited or not. On this one, we observed hexagonal crystal structure of the zinc oxide. But the most important is the morphology. So here you can see that this is the seeded zinc oxide which is having growth perpendicular to the substrate surface. So on the FTO coated glass substrate. And this we have used it as a seeded zinc oxide which can avoid penetration of the liquid electrolytes towards FTO, which can shorten the device. So next requirement it is there, interconnection of the nanoparticle with very high surface area. So zinc oxide we have deposited with very high surface area by using chemical bath deposition. So what we used? We used zinc acetate with hexamethyl tetraamine, just room temperature deposition. Deposition time we have varied maybe 20 to 40 hours. And then also we have annealed that one at 200 degrees Celsius because it contains hydroxide part. And here you can get the clear idea that zinc oxide, whenever you are making on the FTO, it is white in color. White in color means what? It should have the band gap greater than 3 electron volt. So that is the requirement for the dye sensitized solar cell application. So you can have the TiO2 or zinc oxide, it should have the wide band gap material. Means material should have wide band gap with interconnection of the nanoparticle. That is the most important aspect. Am I audible, madam?
Yes, sir.
Okay. So
Yes, sir.
again structure we have identified just to confirm that one. But most important to identify the band gap, because requirement it is it should have the wide band gap, and that zinc oxide should not absorb much more visible part of the solar spectrum. So here from the absorbance against the wavelength, you can get the idea that it is having absorption less than 0.5. So it is not absorbing that much, and we have calculated the band gap by using the formula alpha h nu square versus h nu. And here you can get the idea it is having the band gap greater than 3 electron volt. Means whatever visible part of the solar spectrum it is there, it can pass through this one, which can fall on the dye which is going to be coated on this zinc oxide. Then next approach, you should have the high surface area. Then we have taken the SEM image for this zinc oxide. We observed petal-like morphology. But what we required? We require the interconnection of the nanoparticle with very high surface area. That is the basic requirement. Wide band gap, that is now fulfilled. So second requirement has to be fulfilled. So what we have done? We have done just this image at a higher magnification. And here you can get the clear idea that the zinc oxide that we have grown, it is cactus-like morphology. So interconnection of the nanoparticle it is there with very high surface area. On this one, we have coated monolayer of the die. So this is a cross section image just to get the idea how much thick it is there. So you can this it is embedded with the nano, that is very small size of the particle, but thickness is very high because very high surface area it is required. And this was published inside Journal of Alloys and Compound. And here you can get the idea zinc oxide with different type of the morphology that we have performed by using just chemical method called CBD as well as CLR, room temperature as well as high temperature, with different precursor like zinc acetate, zinc nitrate, and combination of CBD and CLR. So here we got nano beads, nano pairs, then hexagon, nano rods, different type of the morphology we have achieved, and that we have reported in the Gelcom journal just by using simple solution chemistry approach that can be useful for different applications depending upon your target application. So next approach it is there, dye adsorption. So this zinc oxide coated on TCO, we have used this one, we have dipped inside the ethanolic solution of the dye. So this dye gets adsorbed on the zinc oxide by chemical attachment. So whenever you are working on the dye sensitive solar cell application, if you are using TiO2, you should have the dye with NCS group. But if you are using zinc oxide, you should have the dye with the carboxylic group. That is the most important criteria. So you should understand whenever you are making the device, what are the criteria or what are the requirements are there. So that is the most important. Then what we have done, we have used liquid electrolyte as a polyiodide. Then by using capillary reaction we have placed and platinum as a back contact that we have developed. Then we have completed this device. Initially, we have used the evosin Y as a dye. So evosin Y contains carboxylic group. So this is from the xanthanum series, and this you can think whether it is costly or not, because this dye we are using in the micromolar, and this dye may be about 1 gram, you can get about 900 1000 rupees. So from that one we are using micromolar solution, so very less quantity that we are using. So zinc oxide, it is white in color. When you adsorb this evosin Y, which is red in color, this zinc oxide get converted into the red. So we have calculated the absorption against the wavelength, and you can see that evosin Y having smaller absorption. It is from 500 to 550. Very narrow absorption it is there. But another advantage is that it is red in color. So you can think of to use this zinc oxide with evosin Y to make the solar cell which is red in color. So just I am going to demonstrate that one. So this is the efficiency versus different primitive parameter we have optimized. This is for area 1 centimeter square. And here you can see that although we are making the electrolyte between this zinc oxide with evosin Y and platinum as a back contact, we have just used crocodile pin. And this we have tested for almost 1 month. Just we have added electrolyte in between because there is no perfect sealing, still it works very well. And we got the efficiency about 2%. Although evosin Y, it is having very narrow absorption in the visible part of the solar spectrum. And here you can think about the energy band requirement for evosin Y as well as the zinc oxide, because this is the most important requirement. Energy band diagram should be fulfilled. Then evosin Y should have carboxyl group, that is also fulfilled for because we are using zinc oxide. This was published inside the journal Solar Energy. All parameters you will get for the PPT parameter inside this one. Then next approach to get more absorption, we have used another dye called D149 dye, which is having also carboxyl group, but here you can see that absorption region it is more and it is brown in color. Added advantage is that efficiency we have reached close to 3.5% by using simple chemical method. That is the beauty of this one. This was also published inside the material letters. You can get all the parameters here. Now you can think about what are the colorful approach that we have established in the laboratory. So evosin Y, it is red in color. Then coumarin 343, it is yellow in color. Methylene blue, it is blue in color. So we have adsorbed on the zinc oxide. So absorption we have taken for each dye. You can see that methylene blue dye, it gives very high absorption. But this methylene blue dye, it is not having carboxylic group, but it is having chromium group. But coumarin 343, it is having carboxylic group. It attach very well on the zinc oxide, and here you can get the photo image of the zinc oxide, red color, yellow color, and blue color. And because of the not having carboxyl group, although it is having high absorption of the methylene blue dye, it gives very less efficiency. And coumarin 343, it gives efficiency above 1%. So because of the intrinsic property of its absorption and chemical attachment, each dye can give its own efficiency. Then advanced colorful approach that we have done, Now you can think we have three color in our hand. One is red, second one is the yellow, third one is the blue color. Now you can think we can have the red color and we can have yellow color and blue color. Why not to mix two color to get the third color? So we have used this one because we have mixed the red color with yellow color to get orange color. If you are mixing yellow color with blue color to get green color, and if you are mixing red color with blue color, you can get the violet color. So just by mixing means that is called as a cocktail dye or blended dye. So we have tried this one for red color and yellow color to get the orange color. We have adsorbed on the zinc oxide, and this is the orange color dye adsorbed on the zinc oxide. Whether we improved with the efficiency, that is one question. Second one, we get the orange color. We get the orange color in our hand. That is the beauty of this one. So what we have done is by mixing the red color with the yellow color to get the orange color, we have mixed this one and we have adsorbed on the zinc oxide to have the solar cell. So here you can get the absorption against the wavelength. You can get the idea that orange color dye, it covers the both the part, yellow color as well as the red color. Because yellow color it is mixed with the red color, so it gets the orange color. It covers the both the part, and this is the quantum efficiency against the wavelength. This is for the completed solar cell. So here not only orange color that we got, but efficiency improvement also we got for the blended dye. That is the added advantage. Not only this one, we have done for different dyes like rhodamine B, rose bengal, mercury chrome, N79 dye. Each dye you can see that it is having a different color. So you can have the red color, you can have yellow color, you can have the blue color, you can have the brown color, you can have the pink color. So it is possible to fabricate the solar cell with a different color. That's why the title it is made as the colorful dye sensitized solar cell. So that is fabricated in the laboratory by using simple solution chemistry. And this was also published inside the Journal of Photochemistry and Photobiology A, so that there is a boost in the efficiency. So what the achievement we have done? This is the efficiency calculation by using instrument. But I want to demonstrate that one how it is working. Here you can see that this is a calculator and digital watch it is there. As each cell gives 0.5 volt, for one device we require 1.5 volt. So without any perfect sealing, just because of the crocodile pin, we have connected this one in series, 3 cells to give 1.5 volt. And this one we have run the calculator as well as digital watch by lab fabricated dye sensitized solar cell. So that is the satisfaction you can get. And here I want to demonstrate this one. Can you see this video? Yes, is it?
Yes. Yes, sir.
Once again, I can play this one. So this is in dark and light. You can see without any perfect sealing, this device is working very well. Just chemically bath deposited zinc oxide with nano materials. So you should have the satisfaction at the end. Paper publication, it is another part. So this works very well. So next approach it is there. Cellar it is there. We can skip this one. So cellar here we have used to make the quantum dots. Just give the example that cadmium sulfide we have coated on titanium dioxide for solar cell application, and we have used this cellar method to make the solar cell. Here what we have done, we have coated titanium dioxide by using spin coating technique that I have already demonstrated. Then cellar method, that is just dipping technique it is there, we have used, and we have varied the number of cycle as 8 cycle, 13 cycle, 15 cycle as well as 20 cycle. So we have done the X-ray diffraction pattern just to calculate the size of the particle, and you can see that with increasing the number of cycle, size of the particle it increases. In a reverse way, if you are having lesser number of cycle, size of the particle it is smaller, and you can see that the size of the particle is less than 10 nanometer. Means these are the quantum dots of the CDS. It is grown by using cellar method on titanium dioxide. And this is absorption against the wavelength. Black color it is for TiO2, and here different CDS it is there with the different cycles. You can see that band gap variation it is there, and that it is possible to view by using naked eye as well. So 8 cycle having smaller size and 20 cycle it is having bigger size, so that it gives more darker and darker image. This is taken from the back side. Titanium dioxide it is white in color and CDS it is yellow in color. So you are getting the CDS with the different size of the particle. And with a different variation of the cycle, we have taken a CM image. And here you can see that this bigger ball it is there, it is a TiO2, smaller dots are there, these are the CDS nanoparticle, or you can say quantum dots. With the increasing the cycle, you can see that agglomeration of the particle it is there, and size it is going to alter, and it can increase. And for 13 cycle, just to get idea, here bigger ball it is there, it is TiO2. So in order to confirm that one whether quantum dot it is formed or not, we have taken high resolution transmission electron microscopy. In the second image, you can see that this is TM image, and these darker spots are there, these are the CDS quantum dots coated on the CDS. But still here we cannot say whether it is CDS or whether it is TiO2 or not. In order to have better confirmation, we have done HRTM analysis, and here this scale bar it is 5 nanometer. So here you can see that this bigger ball having planes oriented in one direction. These are the TiO2 nanoparticle from the Degussa company, having the average particle size about 25 nanometer. And the smaller circles are there. This is the CDS quantum dots, which is grown on the titanium dioxide nanoparticle. And here you can see that size is about 5 nanometer by using CILAR method. And the particle size it is very uniform, 5 nanometer or 6 nanometer it is there for this CDS. So it is possible to fabricate quantum dots by using simple dipping technique called as a CILAR technique. So you can use this one for solar cell application. Not only here, at the end here you can see that CDS it is having band gap 2.42, but with the increasing the cycle, band gap can be increased, but with the decreasing cycle, band gap it is lower, right? And here you can see that although it is having a larger band gap greater than 2.42 electron volt, it works as a solar cell. So instead of dye, CDS we have used as a sensitizer, and it gives the efficiency about 0.6%. Efficiency is not so high, but we have fabricated the quantum dot just at a lower temperature by using simple CILAR technique. So you can work on the quantum dot as well to grow the quantum dot by using CILAR technique to have the different application. So this was published inside the RSC Advanced Journal, Solution Process CDS quantum dots on TiO2 for the solar cell application. So next approach it is there called supercapacitor. How much time it is there, madam?
Sir, 20 minutes more.
20 minutes. Okay, madam. So supercapacitor, it is one application where it is called as a electrochemical energy storage, which has having higher energy density than the ordinary capacitor and higher power density than the battery. Energy means what? It is the capacity to do the work, and power means what? How fast energy it is delivered. So we can understand that one by using Raygon plot. So this is power density against the energy density plot. So batteries it is having higher energy density, capacitor it is having higher power density. So supercapacitor lies between the capacitor as well as the batteries. So we can understand that one on the basis of the parameters called charging time, discharging time, energy density, power density, cycle life. So supercapacitor parameter lies between the battery as well as the capacitor. Capacitor can quickly charge in millisecond to microsecond, but battery requires certain minutes to hours to get charged. But supercapacitor it can charge within certain minutes, and also for discharging also it can discharge within certain minutes. So whenever application it is there, for that type of the application you can use the supercapacitor. But nowadays you can see e-vehicles are coming with the battery. So battery, suppose it can have the cycle life about suppose 2000 to 3000 cycles, but supercapacitor it is for example 10,000 to maybe 1 lakh. And if it is possible to have energy density of the supercapacitor comparable to the battery, it is possible to have in the future instead of battery you can use the supercapacitor, so that it can run for longer time, because battery can withstand maybe 3 to 4 years. So supercapacitor maybe it can withstand up to 10 to 15 years. That will come in the future. Not only this one, just as an example, one bus is running in Shanghai based on the supercapacitor, but it is in the liquid form. So at the one station, when people are riding inside this one, people are riding inside this one. This just one moment, talk is going on. So when people are riding inside the bus, this supercapacitor gets charged, and during its travel it can discharge. Again in the next stop, again it can be charged. So here, if your bus is running for example 5 to 10 kilometers, right? We can use this type of the super capacitor at present days. So in the future, if it is having energy density comparable to the battery, it is possible to replace these batteries by using the super capacitor. Not only this one, nowadays lot of applications are coming go up, like a flexible type of the electronics, variable type of the electronics, where you require the energy storage device which can be flexible. So we thought to make flexible super capacitor and completely solid state super capacitor, because if it is liquid, it is there is a sealing problem is there. So if sealing problem, you cannot bend that one, that is the issue. So we thought to have the solid, completely solid state super capacitor, so it can be flexible as well as solid state. So basically, if you are thinking about the super capacitor, there are two types. One is called as the EDLC and second one is the pseudo. So for EDLC, mostly carbon based material it is used, and the mechanism it is same as that of the capacitor. And in the pseudo, surface reaction it is there called as a Faraday type of reaction it is there. So mostly metal oxide, metal polymers, metal chalcogenide it is going to use for the super capacitor, so pseudo type of the capacitor, and it is having the same principle as that of the battery, but each is having its own advantage as well as disadvantage. EDLC is having high stability but low capacitance, but pseudo it is having high capacitance but low stability. So what we thought to have the hybrid one, which is the combination of the both, having the EDLC as well as the pseudo. So what we have used, carbon nanotube with metal oxides or polymers. Carbon nanotube belongs to EDLC, metal oxide or polymer it belongs to the pseudo, so that it can have an improved electronic conductivity, well directed path, dual charge mechanism. So basic requirement for the supercapacitor is that it should have the high conductivity, large surface area, good chemical stability, good reversibility, and higher valence state, or we can say oxidation state it is required. So whenever you're thinking about to improve the energy density, which can be comparable to the battery, you should work on the increase the capacitance through this parameter like specific surface area, porous size, electrical conductivity, and redox reaction. And if you want to increase the voltage, that is the potential window, you can work on the organic electrolyte or ionic type of the liquid electrolyte, asymmetric or symmetric type of the supercapacitor. So what we have done, we have focused with the different surface architecture. So we have taken stainless steel as a substrate, which is commercially available in the market. We have quoted different type of the morphology like nanoflex, nanoparticle, nanowire, quantum dot, core shell, as well as carbon nanotube on the stainless steel substrate. As carbon nanotube it is there, it is having EDLC. So we thought to make hybrid by coating pseudo type of the material like nanoflex of the metal oxides or metal sulfide or metal chalcogenide, nanoparticle or quantum dot or polymer on the carbon nanotube. So we have used simple deep and dry coating technique that I have already demonstrated. I can skip this one to coat the carbon nanotube. Then we have coated vanadium oxide, carbon nanotube it is a EDLC type, and we have coated vanadium oxide by using simple chemical bath deposition technique to make the symmetric supercapacitor. Symmetric means what? It is having both the electrode of the same type. So simply we have used chemical bath deposition technique, vanadium oxide with ammonium hydroxide solution we have made at 60 degrees Celsius. Carbon nanotube coated stainless steel substrate. We have dipped inside the solution and it was coated on the carbon nanotube as a vanadium oxide. Here you can get vanadium oxide whenever you are coating on the stainless steel, this flex like morphology. But whenever you are coating on the carbon nanotube, it gives flex as well as very high surface area. That is the beauty of this one, that we have coated vanadium oxide by using simple chemical approach, flex, nanoflex of the vanadium oxide on the carbon nanotube. And here you can get the TM image, so that this flex like morphology you can see outer surface area of the carbon nanotube. Then we have used 3 electrode system to study the electrode and 2 electrode system to make this to check the performance of the solid state device. So what we required, you have to see the IV curve called as a current versus voltage, called as a cyclic voltammetry. So we required to have the current versus voltage graph. For the black color it is shown for the carbon nanotube, red color it is for vanadium oxide, and blue color it is shown for the hybrid. And area under the curve, when area it is more, charge storing capability it is more. And here you can see that from 0 to 1 volt it gives the potential window, means whatever the voltage it is there, it is taken by that device, right? So here you can see that carbon nanotube when we are coating with the vanadium oxide, its area under the core increases, so that its specific capacitance increases for the hybrid, so that it gives about 150 farad per gram for the vanadium oxide coated on the carbon nanotube. And we have done this one with respect to the scan rate as well, and we achieved very high value of the specific capacitance above 1000 farad per gram at 2 millivolt per second. And this is the formula that we have adopted, specific capacitance equal to this one. Next one, this is for the electrode. So we have tested this electrode for almost 4000 cycles, and we observed that it is showing 93% stability for charging, discharging, charging, discharging. That is a CV cycle. It is there that we have adapted for 4000 cycle, and it is very, very stable. And here, then we have done this one as a solid state device. So what we have done, carbon nanotube coated on the stainless steel as a one substrate, which on which vanadium oxide it is coated. This is one electrode. Then similar electrode we have taken, and in between we have embedded lithium perchlorate, where lithium ions are conducting, and PVA, it is a non-conducting matrix. So this lithium ions embedded in the non-conducting matrix, we have embedded inside these two electrode, and then we have made the gel, we have inserted inside between these two electrodes sandwiched together. Then we have pressed that one for overnight, and then it is completely dried. So this is the image, 3 by 4 centimeter square complete solid state device that we made in the laboratory. And also we have, you can see that this is flexible. Flexible means what? It is possible to bend mechanically. So this is a flexible device that we made in the laboratory by using simple solution chemistry. And here you can see that because of the symmetric one, it gives the potential window about 1.8 volt, and also having very high capacitance about above 460 farad per gram at 2 millivolt per second. And we have tested almost for 4000 cycle. It gives more than 95% stability. This is better than the single electrode. So solid state device, it is having better stability of 96% for 4000 cycle that we have achieved in the laboratory. Not only this one, we observed energy density as well as the power density. For this one, we have calculated by using Raygon plot. And here we can tested this one with a mechanical bending as well, because just I said it is a flexible device, so that we must test with respect to bending. So we have tested this one up to 175-degree mechanical bending, and it is 90% stable. Not only this one, we have tested almost 7 days. And we have used this 3 by 4 centimeter device to run VNIT panel. This VNIT panel consisting of 21 red LEDs, and we have run by using single device. By charging less than 1 minute, it can run up to 6 minutes. So that is the device made by using simple solution chemistry based on the nanoflakes of the vanadium oxide coated on the carbon nanotube. This was published, vanadium oxide on stainless steel, in the Electrochemica Acta, and vanadium oxide coated on the carbon nanotube. It was published inside the Nature Scientific Report journal. And here I can just give the demo for this one. This was also made in the paper. Also, I have demonstrated this one in one DST. They called for the meeting, and they were given the booth. I showed this one to Saraswati Niti Ayog member, Secretary DST Ashutosh Sharmaji, as well as Ram Gopal Rao, Director IIT Delhi, and we have demonstrated this working model for this one. And here you can get the clear idea. This is the device we made in the laboratory. Now this is charging with 3-volt battery, and now we are discharging this one through the VNIT panel consisting of 21 red LEDs. Video is visible, madam?
Yes, sir.
So you can get idea how the simple solution chemistry as well as the nanomaterial is very helpful for making the device. You should not only think to make synthesize the material in the laboratory, not to just characterize, but you have to apply for the device grade application. So it can be applicable for the society. That is the most important part that I want to elaborate inside this talk, and how these simple chemical methods are much more useful, because without much sophisticated instrument, you can work on the nanomaterials. So that is belongs to the nanotechnology. So next one, here just to get idea, we have used this uh, panel to run one small fan. Here you can see that this is charging. Now this is discharging. Within charging of 30 seconds, It can run more than 3 minutes. Without any sophisticated instrument that we have developed in the laboratory, this solid state device, which is a solid state as well as flexible. Not only this one, we have made different devices, and here these are the parameter for different solid state devices. You can go through my Google, you can get different materials as well as different devices. Also, we are working on room temperature gas sensor. I'm not going to elaborate that one, but we worked on this room temperature gas sensor, which is a LPG sensor based on the heterojunction mechanism. Most of the metal oxides are there which can operate at a higher temperature, but we developed the device which can work at the room temperature by using simple solution chemistry. We have made two layers. One is N type, another is P type, or NN or PP type, so that there is a heterojunction or a heterostructure, so that at a specific voltage value there is a change in the current, so there is a change in the resistance, so it can work on the change in the resistance mechanism at just room temperature. So we developed this one in the laboratory. Just to get idea, we have developed CDS nanowire coated with polymer and given contact, and this can work as a room temperature gas sensor. So that's all. We can say nano can play a very vital role for energy and environment through the soft solution chemistry, so that we can work against the global warming. Thank you very much.
Hello. Thank you,
Hello.
sir. The session is now open for the question and answer. Participants may write the questions in the question answer section.
Hello, Divya ma'am.
Yes.
Ma'am, one question from my side also.
Yeah, ma'am. Please, you
Yes.
can ask.
Sir, what is synergetic effect? Can you please explain some?
Yes, energetic effect means what? For example, if you are working with the carbon nanotube, just one EDLC and one pseudo, so it will take advantage of the both.
Okay.
So it is a material mutualism, we can say.
Okay. So how it's work on nanomaterials?
Nano means what? For example, if you are having nano, size is very small. For
Yes.
example, for a supercapacitor application, you require very high surface area. If you are making very big size particle, surface area may be lower.
Yes.
So if size is smaller, you can quote, for example, on carbon nanotube whole surface area, outer surface area. So interface is there, which is more in case of nano as compared to the bulk material.
Sir, any book can you suggest for
Uh,
this particular subject?
yeah, this is book I already written. This one I can share. This one I showed this one. Can I share this? This one you can write it down, where
Okay.
13 chapters are there, and among which 12 chapters it is devoted to the simple chemical methods, where we have done hydrothermal, electrodeposition, spray pyrolysis, spin coating, screen printing, doctor blade, electrolysis, spray, CLR, CBD, like that one. But not only this one, we have given preparative parameter, synthesis part, characterization some part, as well as application part, like gas sensor, supercapacitor, solar cell, some electronic transistor. Also, we made some using chemical method.
Okay. Actually,
But
my interest on wastewater treatment from nanotechnology, so that nanomaterial. So
yes, you
that's
can
why.
make the material either in the powder form or maybe in
Mhm.
the thin film form, and so that it can be used with very high surface area.
Okay. So that's why I want to search and I want to develop knowledge about this. So that's why I'm searching best book.
Yeah.
So any this book
Then
is
this may be very good book for
okay,
you,
sir.
maybe. Yeah.
Okay. Okay. Thank you so much.
One more question is from Mr. Saurabh Singh. What is capping agent?
Capping agent means what? Suppose here we have not used any capping agent, but capping agent can serve to restrict the size of the particle. So
Hello,
if you want to inhibit the growth of the particle, you can use the capping agent.
sir.
Yes.
One more question. Hello. Yes, sir.
Yes.
In particular, in gas sensing material, which is a better material as a particular used in the metal oxide,
Yes.
in the form of thick film, thin film, or pallet, which will be better material for gas sensing
No.
purpose.
Instead of that one, you can think another way. The material which can give the very high surface area. One thing. Second thing, the material which can sense the gas at lower temperature. That is, we can say, better material.
And then upon which form,
No,
particularly thin
form
film,
can be
thick film, or
nanoparticle.
pallet.
It can be no pallet. Whatever pallet.
No, no,
It, in the just 1 minute. In the pallet, you are using lot of
uh,
material, right? In the thin film, whatever
yes.
material it is there, that material quantity is very lesser. So if you want to make the material in the lower quantity, it is better, or higher quantity, it is better.
Which is a better, sir?
Lower always it is better, because cost issue, if you are making the material with a very high quantity, cost issue it will be higher.
In the form of nanomaterial,
Thin film it is
then
always better,
thin film is in the
but
form
it
of
should
thick
have
film.
uh, thick film material cost, investment of the cost, it will be higher in the thick film or pellet.
Yes.
Suppose if you are using the material, right, one material if you purchase 1 milligram, another material it is 1 gram, where cost issue it will be more, 1 gram it will be drastically more, right?
And any instrumentations are available for the gas sensing studied.
Yeah, there are different companies are there, they are having the instrumentation fabricating, but still you can develop in the laboratory as well. We have
Oh,
developed
sir.
in the laboratory.
Oh, sir. Mistake.
Thank you, sir.
Thank you, sir. Thank you so much, sir, for sharing your profound knowledge with us.
Thank you.
Now I request Dr. Kavita Sharma, Professor, Department of Chemistry and Convener, Faculty Development Program 2024, to kindly offer her concluding remarks for today's session. Ma'am, please.
Thank you, Vidya. Thank you. Good evening, friends. Today, Dr. Babasaheb R. Sankpal from Department of Physics, Vishveshwaraya National Institute of Technology, VNIT, delivered his lecture on colorful solar cell and flexible solid state supercapacitor state of art to nano. And later, he covered nano embedded thin films, advanced applications towards energy conversion and storage. Sir started by sharing his research group. Congratulations, sir. 16 students completed their research work under your guidance. Congratulations.
Thank you.
Congratulations for getting funded projects around 3 crores also.
Thank you.
Also would like to congratulate you for the book authored by you on simple chemical methods for thin film deposition, which will be very much helpful for the budding researchers.
Yes.
I'm sure. Sir gave very good punchline. Chase quantum, nano will follow you. I really liked it. Very correct. All researchers must follow it. He discussed simple and low cost chemical methods, discussed bottom up and top down methods in very simplified way. As we all know that energy crisis is main issue that whole world is facing. I'm sure all of you are agree with this. That's why today's session is very much important for all of us. Sankpal sir is working on energy conversion to photovoltaic and energy storage to supercapacitor. Sir shared that if solar cells are colorful and attractive and supercapacitors are completely solid state and flexible, then they will have added advantage. What we have understood today. He discussed the most recent simple and low cost chemical routes from synthesis of nanomaterials to device grade applications. And for the development of colorful dye, sensitized solar cells, Q dot sensitized solar cells, and flexible solid state supercapacitors, which have wide future applications very effectively. So, outcome of his lecture is try to do simple things in simple way, learn more and apply more complicated things by simple way, and most important is that should be applicable or useful for the society. So I'm sure all the researchers, all the faculty members will keep it in mind and will continue their research accordingly. And if you need any help from Dr. Sankpal, I'm sure sir will always be with us for sharing his knowledge with us. So thank you, Sankpal sir, and thank you, participants, once again. So I request Divya ma'am to call some of the members who are attending faculty development program since 22nd, because today is the last session of our faculty development program. So anyone
Okay.
of you? Yes.
I'd like to call Dr. Goshir Uddhav Dahinat sir from Shri Trilok Jain Vidyalay, Pathari, Ahmednagar, Maharashtra, for the feedback.
Is he here?
May I call Dr. Shweta Hingwasia, Assistant Professor, Government MLB Girls PG College, Bhopal, for the feedback.
Hello, I am audible.
Yeah, you're audible.
Yes.
Okay. I am very thankful to Vaishnav Vidyapit Institute University for organizing such an informative and innovative FDP on nanotechnology and its application. It's such a broad aspects of chemistry. And as you know, the more you wish to know about this subject. The basic of FDP is to learning never stop, and this is proven by the all the eminent speakers by providing us a lot of information with their well explained animated PPT. And I am thankful to all the moderator, especially Dr. Kavita Sharma madam and Radha Mehra madam, because she because she not only help us on Zoom meeting, but uh, also with on a WhatsApp group. Really, I learned a lot. Again, I thanks to all of you and request to university to organize such a beautiful program to increase our knowledge. Thank you.
Thank you, ma'am. Thank you for the wonderful feedback. Now I request Dr. K.V. Goswami, Assistant Professor, Department of Chemistry, the HNSP Limited Science College, Himmatnagar, Gujarat.
Hello.
Yeah, you're audible, sir.
Okay. Good afternoon, everyone. Myself, Dr. Goswami from Gujarat. First of all, it is nice opportunity to attend the FDP on nanotechnology and its application. In this, all 5 days, all eminent speaker deliver their knowledge with research works in a field of material science and especially in energy, which is the most requirement of this globe. So first, Dr. D.V. Prabhu give the blessings for the success of this FDP. And first day, Dr. Subrata Bhattacharya sir. Second day, Dr. Simpi sir. That Dr. On third day, Dr. Mungir sir. Fourth day, Dr. Venkatachalam sir. And today, Dr. Sankpal sir deliver a very nice lecture. And a very interesting part is the dye sensitized solar cell and solar methods. So we enjoy this whole lecture. My college team also enjoy this lecture, and we learn lots of from this FDP, and will imply to our research students and our master degree students for the to get the interest in the nanotechnology. So I am congratulate for this nice success of this FDP, whole team of SVVB, and special to Sharma ma'am to give me this opportunity to give my feedback. Thank you very much, everyone.
Thank you, sir. Thank you so much. Now I request Dr. Kavita Sharma ma'am to propose words of thanks.
Friends,
Just shall I take the opportunity to express my views?
yeah,
Yes,
sure.
sure.
I'm Dr. Bhavani from Excel Public School, Mysore. So, from the first day, from 22nd to 26th of April 2024. So, thanks first the university for conducting this faculty development program. Though I have completed my PhD in the nanotechnology, I had a long break. I thought this FTB will serve as a refresher course for me. The first day it started with a technical glitch. Then it was solved immediately. Dr. Guru Prasad sir taken the initiative and he solved in situ. He solved the issues. So it started with a welcome address by Guru Prasad sir. It's such a motivation. He explained what is the need for this FDP. The lot of knowledge is there through Google. What is the necessity for this? So he clearly mentioned that interaction with the experts makes clear, which Google cannot give. So followed by Chief Guest Address, Dr. D.V. Prabhu. So his speech motivated us as if we have to publish some papers in the journals, Indian journals. That motivated us a lot. So started first with Dr. Subrata Bhattacharya. So he started with some elementary steps in nanotechnology. He discussed about the synthesis of nanoparticles and how it is used as a photocatalyst. The second day, Dr. Shimpi, it was a really interesting seminar where he focused on synthesis of core shell nanoparticles and application in photocatalyst as well as the wastewater treatment. So then continued Dr. Aravind Kumar. So his work, his industrial work is highly impressive. So he discussed about the hybrid sensors and semiconductors. And the fourth day, that is yesterday, Dr. Venkatachalam. So the day started a little with, okay, what we will do with FTR spectroscopy. I was thinking when I logged into the session, but he discussed very basics of FTR spectroscopy and he started to interact with us more. So it was a very interactive session with sir. And today, the last session that deals about the photo sensing material. So I really thank the organizing committee for giving me the opportunity to share my feedback. So we expect a lot such faculty development programs so that it is useful for the place where we are working. Though I working at the school, I can implement some of these principles. For example, sensor, I have gone some information about that. I can implement in our ATL labs so that it will be useful for other students. And at last, I thank all the moderators who have done the excellent job throughout the session. Thanks a lot. Thank you, Kavita Sharma ma'am, for giving this opportunity.
Thank you, Bhavani. Particularly, I'm so happy to know that not only college faculties or university faculties are attending the FDP, also school teachers have registered themselves and attended full sessions. So, thank you very much. From school level, you will be giving knowledge to school students and motivate your students from school level. It will be very much helpful for all of us at higher education. So thank you. So I'll take 2 more minutes to propose words of thanks. So friends, it gives me immense pleasure and gratitude to extend my heartfelt thanks to each one of you for making this 5 days faculty development program on nanotechnology and its application an outstanding success. First and foremost, I would like to express our sincere appreciation to our esteemed speakers, Dr. Subrato, Dr. Shimpi, Dr. Mungre, Dr. Venkatachalam, and today's speaker, Dr. Sanpal, whose expertise and insights have enriched our understanding of nanotechnology and its diverse applications. Their dedication and passion for sharing knowledge have truly inspired us all. Thank you, sir. I extend our heartfelt gratitude to Dr. D.V. Prabhu, ACT Secretary, for the collaboration and generous financial support extended towards the success of this program. His commitment to fostering academic excellence is truly commendable. A special words of thanks is also due to our esteemed director, Dr. K. Guru Prasad, and Vice Chancellor, Dr. Upinder Dhar sir, for their unwavering support and guidance throughout the planning and execution of this faculty development program. Their visionary leadership continues to inspire us to strive for excellence. A heartfelt thanks to Dr. Anand Rajawar, Director, Sri Vaishnav Institute of Technology, Sri Vaishnav Vidyapith Vidyalaya, and his technical team, especially to Professor Ashish Anjana and Nitin Sarauge, behind the scene efforts in ensuring the smooth conduct of this faculty development program. Your expertise and professionalism are truly appreciated. I would like to express my sincere appreciation to the Faculty Development Coordinator, Dr. Radha Mehra, for her dedication and attention. Thank you, Radha. Last but not the least, I extend my gratitude to all the faculties of Department of Chemistry, Sri Vaishnav Institute of Science, Sri Vaishnav Vidyapith Vishwavidyalaya for their support and collaboration have been invaluable in making this faculty development program a resounding success. And especially to all the enthusiastic participants, I'm very happy that all of you have joined on time and attended full sessions every day. Your active participation and engagement have truly enriched the discussions and made this FDP a memorable learning experience for everyone involved. In closing, let us carry forward the knowledge and insight gained from this faculty development program to further advanced research and innovation in the field of nanotechnology. Thank you once again to everyone who contributed to making this event a grand success. Warm regards. Thank you. Over to you, Divya.
Thank you, ma'am. Now I request all the faculty members and everyone to please open the camera for the group photograph.
All of you, please turn on your cameras. Thank you.
Thank you, one and all.
Thank you all of you for active participation.
Shall we leave, ma'am? Hello.